So I'll give those to you and I'll give you a funky thing to do as in-class assignments. I have groups set on there, assuming everybody was here. So just, I think you guys got the deal. Like work with someone who you feel like you work well with and can explain things, and we'll also let you do things on your own. All right, so definition number 1. This is for closure. So suppose I have a topological space X and I have a subset of that topological space. Oh, this is not closure, this is interior, sorry. It's both. The interior of A, in your book, I think they use this or this, is the union of all open sets contained in A. The closure of A I would use a little c, he's using a big C, but whatever, is the intersection of all closed sets containing A. So how did you probably defined it in real analysis as closure is a set that contains all its limit points? Or you might have done closure is the set union its boundary. Both, okay. But I mean, you need a metric for that. You need to have you actually don't need a metric for defining a limit point. So you can use just open sets to define that. But for boundaries, you start to have they use a metric. So I think Dr. Clark actually taught real analysis with the topological metric. So you probably use the metric itself to get those ideas across. So a typical topology class would start like that. It would start with doing real analysis with metrics. So you have a distance function and you define your open sets through the distance function. You're basically working on the Euclidean topology with a distance. So you can think of the open interval A to B as being a distance, an open ball. And then you start just using that notion to define everything. But then when you get to generalizations, then it's hard because you're moving away from something you already know, which is metric spaces. And you're saying, okay, I don't need metric spaces. I can define these all abstractly. Dr. Adams' book starts the opposite way. He just starts with open sets first, and then he builds everything up from the open sets, which is really, I think, the way you should think of it.
I don't really understand closure. So A is a collection of sets.
Right.
It's a subset. So
A is just one of the subsets, right? So you go inside A and you intersect all the closed sets inside A.
all the closed sets.
Oh, sorry. You go outside of A and there's a bunch of closed sets. So think of if you want to go to, I think only Tim hasn't had real analysis from Dr. Clark, right? Okay, all right. Right. So let's say you have A to B, right? The closure of this set would contain all its boundary. So the closure is equal to, that's complementary to what he does. Like this. So the way they teach this in real analysis, because you don't have this open set terminology, you would just say it includes its boundary points. Or another way you could say is it includes all its limit points. So you can think of the open interval A to B. If you want to talk about limits in real analysis, you need a distance because you have a distance function in your limit definition. And then you would take, it includes all its limit points or accumulation points, the things that if I have a sequence inside this set, and it limits out to something, that limit also should be in the closure. Right?
That also include like if you've got, some sort of, line from a calculus class, but it's got a bunch of discontinuities. Inside the closure, it would be just the line itself without those discontinuities.
That's correct. The way mathematically we draw it.
Yeah.
You're right, so it has a discontinuity, it just draws it as a straight line. So yeah, exactly that. So you can think of like A and B are not included in this. So little treaties to point set topology, A and B are not included in this open interval. But I can create two sequences entirely within this open interval, A plus 1 over n and B minus 1 over n. Those two sequences are inside here, but when I limit, the limit would be A. So you include that limit. So everything would be inside. So the closure of this thing is this guy. Now, if you use this more general definition, you're thinking of all closed sets that contain A, B. Well, the closed set and then intersecting them down. The smallest thing you would get that contains A, B is the closed interval A to B.
Okay, so the closed sets being the complements of all the open sets. Right, because that's.
Yeah, that's the definition, yes.
The closed sets are all, I want to make sure everything is right, so. The closed sets are all complements of all the open sets, so for that example, like every sub-interval of A to B. Has a complement,
Yes,
and you intersect all those complements. And eventually get to the point where it's like the open interval A B. Its complement is like everything out there. Plus like A, B,
yes.
and then some of those intersections. Right, those intersections all just like make their way down to A.
Yeah, but it doesn't have to be the complement of A open interval A, B. Could be, right, it could be other things. Closed intervals are in the Euclidean topology, closed intervals are closed sets. They're the complement of, you can create a closed set by taking complements of open sets.
Gotcha. Okay.
So it doesn't have to be that set itself that you're taking the complement of.
Oh.
Okay, other questions?
that was-
So John and Michael, you guys took it from, okay, so this is starting to kind of connect up. Connected sets, you probably talked about those too. So these are actually pretty hard to find if you actually had to do them from scratch, because it's hard to imagine what the open sets inside A could look like and union them all up. It's almost like it's another way to think of this is that you're taking the biggest open set that includes this whatever set you're looking at. When you're unioning them up, you're actually taking the biggest gigantic sets you can, and then that is going to be your interior, and then you're covering up the open set with a bunch of closed sets, and you're boiling down to as far as you can go, and that is your closure.
It's like when you blow up a circle, you're inscribing it. So inscribing it, take the big one, put it down.
Yeah, yes,
That's how I.
you're covering it. I mean, I'm using topological words. We're going to talk about covers and things like that in a second, but maybe not this class, but we will be talking about that. Okay. So I gave you an in-class assignment C.
The closure of set, also the interior of the complement of that set. Or the complement of the interior of the complement set.
That's too many. I haven't had my cup of tea yet to think about all that many things, but yeah. The complement of the closure. I'm not sure. You can prove that. Try to prove that.
That seems like something. Okay, that passes the sniff test.
I have to play around with it because there's always like weird exceptions to things, so I want to make sure before I say anything.
Do that a lot.
Hopefully the foundation students aren't listening to these recordings, but I gave them a problem that wasn't true and I asked them to prove it.
So.
Well, I gave it to them. I said, if true, prove, if false, find a counterexample. But of course we're learning how to write proofs. And so they went straight to proving it and they proved something that wasn't true. So. So I actually use these theorems quite a bit. If U is an open set, an X and U belongs to A, is or inside A, then U is contained in, and this might be, yeah. So. That's one. If C is a closed set, that's a bit of what I was saying, that instead of thinking of unions of open sets, you can kind of just take the biggest. By biggest, I mean, it's kind of it's a concept, it's not an actual definition of size or anything. So if C is a closed set, an X, and A is contained in C, then the closure of A is contained in C. I think I used this quite a bit in measure theory, the second one. The third one, if A is contained in B, then the interior of A is contained in the interior of B. To think if he doesn't put any notation for, he just uses subset symbol. He doesn't make them proper or not proper, but Michael's making me think about it. I don't think you can remove that here. So if A is contained in B, then the closure of A is contained in the closure of B. And then next one. So to prove these, they're foundations on steroids. If A is open, if and only if, so that's both the directions is true, A is equal to the interior of A. They're one and the same. And I think I dropped it off, but probably there's a sixth one. If A is closed.
But A and B is the CS part. I gotta get my data types right. So if A and B are collections of sets, because there's.
Collections, just sets. There are two sets that are in X.
Okay.
And
Is that supposed to be like the first symbol up there? It says there's subsets of.
X, yeah, so they're just two subsets of X. They're sets,
X is listed. Okay,
right?
so
So they could be, I guess, a collection of sets, but they're subsets of X.
then would it be more accurate to put it as like a element of, because
No, it's not,
No.
it's not the topological space. It's not T, it's X. X is like R.
X is a set that we're making the topology on.
oh. Okay. Cool, yeah, that works.
The topological space is X, the topology is two.
I never knew that.
So a shorthand way of getting out of writing a T, scripty T now, it's like, just let X be a topological space, the T is implied.
That makes more sense.
All right, I gave you an in-class assignment to. Actually, I think the first one, number 2, you can take our favorite example, and we didn't do C for part 1, so I think I'm gonna, for the rest of the time, I'm just gonna have you guys play around with stuff. Let me pull open the homework before I let you work on things. But you should finish C, actually seeing if this is Hausdorff or not, the digital plane topology. And then too bad the pictures are all gone. And the next thing is to actually look at closed sets, closures, and interiors for something that's very simple looking, but not straightforward. And then take it to something that's a little bit more hard to look at. So I have it set up with not having foundations. I suppose if you really can't do one and you run out of time, it hurts me to do that because that's not how I would do a topology class, but if you run out of time, just do number one on that one. So that's your light. This is what I normally would assign. This is the light and this is normal. I think one is pretty trivial, but it gives someone like you that chance to work with how to improve things when you have unions. It gives you that definition. I don't think we've ever defined union and intersection in here, have we? I might not have. So you might want to get that definition today. The second one, it's just working with a different topology. That was what this one I wanted to give you an example of something that's a different topology that you haven't seen. Right, so take your pick. Good. Well, that's why I have some examples for you to play out.
So we're doing the Hausdorff one?
Yeah, do the Hausdorff one first, because I want to finish that one. It's not, I'll just tell you, it's not Hausdorff. It kind of, you can feel that it wouldn't be. The digital line topology messes up, so you kind of can see why that would mess up. And the other ones I think are tricky because you have to really think about it.